Hi there. In this video, I'm going to talk about the basics of working with floating point registers in YASM x86-64 assembly, or YASM AMD 64 assembly. If you don't already know how to write basic assembly programs in YASM, see my other videos. This video is only going to focus on floating point registers. So for starters, what the heck am I even talking about? If you have assembly knowledge up to this point, which hopefully you do if you don't see my other videos, then you know you can have some registers like RAX and RSI and RDI and sort of move them around with instructions. Let's move R12 into RSI, and you can add two registers together and so forth. You can do a lot of instructions and you can store them and whatever. You also hopefully know by now that the first integer argument for creating your own functions in assembly or calling on other functions outside of your assembly module, respecting the ABI, should have RDI and RSI as the first and second arguments, and then I think it's RDX, and then I think it's RCX after that. But basically, you use integer registers for integer arguments. So keep in mind, we're going to start using floating point registers. In another video, I'm going to totally talk about mixing arguments and return types. But for now, I just wanted to say this. Suppose you have a function in C, let's call it f, and it was going to return a double. Let's say maybe we have like a double D equals like 5 point whatever. And then you want it to return the double D. So then that means the return type here would be double. What this means is that function f, it would not return its value in RAX, the normal integer return value register, because for floating point operations, we have to use a whole different set of registers and a whole different set of instructions to manipulate them. It just doesn't work with the general purpose register. So we can't actually, in assembly, we can't actually return a floating point value using RAX. We have to use one of the floating point registers, and the one it's going to be is XMM0. We have 16 floating point registers. That's the very first one. XMM0, ironically, I guess, is always the very first floating point argument register, as well as the return register. So keep that in mind. I'm going to do another video about that soon. But for now, we're going to return an XMM0. It's important to understand that we have XMM0 through XMM15 to work with. So we have like a lot of floating point registers. None of them are Callee-Saved per the ABI. So anytime you make a function call anywhere, you should probably assume that your float registers have been destroyed already. Kind of inconvenient if you're trying to program for performance. But of course, you can save those to the stack or to memory or whatever. I'll show you that in a coding example after I talk for a little bit. Note also that all of the floating point registers here are 128 bits. The system supports 256 bits, but we're just going to use the 128-bit floating point registers for now. You hopefully are wondering, why do we need 128 bits if all of our floats are usually doubles or singles that only use 64 or 32 bits? Well, this just sort of allows us to do a lot more if we wanted to. In this video, I'm only going to use 64-bit floating point numbers, so just understand that when we use these registers, we're actually only using the lower 64 bits. We're not using the entirety of these registers. Let's see, what else can I say? Let's pull open a wonderful textbook that I love to show. I did not write this textbook. This textbook is by a wonderful professor named Ed Jorgensen, PhD. And he has this book called x86-64 Assembly Language Programming with Ubuntu. He releases it for free, so you can literally just go to his website and download a copy of this book. That's one of the reasons why I love featuring this book at all costs when it comes to assembly. But anyway, so get a copy of this book and you can really turn yourself into an expert just by reading it. Anyway, let's assume that you have a copy of this book, or maybe you just want to follow along with the video, which is fine. Let's go to section 2.3.1.6. So if you look over here on the left tab area, I'm going to click on Architecture Overview. And then if I expand that chapter, I can go to subsection 2.3, which is called Central Processing Unit, and then subsection 2.3.1, CPU registers, and then section 2.3.1.6, which is labeled XMM registers. The reason we're going this far deep, by the way, I love a book that organizes their chapters this way. The reason we're going this deep is because we just want to see the XMM registers or the floating point registers. You can see on this page right here, just as I promised you, we have 128-bit registers and they start at XMM 0. They go all the way up to XMM 15. So just keep in mind there's an earthquake right now while I'm recording this video. I'm going to die. I'm going to die. I'm going to die. No, I guess I'm okay. Did the camera shake? I promise I wasn't faking that. I can't wait until the posts on social media tomorrow when people post like a chair and it's like turned over and they say, "We will rebuild." Luckily, I guess I was away from the epicenter. If you were next to the epicenter, I'm sorry. I hope you're okay. Okay, so we're at 2.3.1.2. It looks like the number is abbreviated over here for some reason. Oh no, because I clicked the wrong thing. 2.3.1.6. Oh, because I scrolled down. That's what happened. Just to show you, where the registers are listed in this textbook. But like I said before, we can't use the same instructions that we used to use for integer registers or general purpose registers. We have to use a whole different set. So I'm going to collapse all these chapters here, and I'm going to open up chapter 18, which is entitled Floating Point Instructions. I'm just showing you this as a reference. I'm going to write some code for you that kind of uses the registers, but I want you to know anything that you need to do with the floating point register, whether it's like, operating directly on a floating point register or, using two together to multiply or whatever, or converting between integers and floats, which you probably want to do. Transfer data from a general purpose integer register to a floating register or back and forth. All that is in chapter 18 right here. I'm going to show you a lot of it. I'm going to show you almost all of it in the code. Not really 100%, but Anyway, so you can see at the top, it just kind of like describes, that we can do control instructions and so forth. The values are 64 or 32 bits. We have double precision and single precision floating point numbers. If you've seen my other videos, you understand how floats work. We know about the registers and data movement. Okay, so the first thing I want to show you is notice how we have to use a different instruction to move data between floats. So, before when you moved data with just integers, you had move R12, and R13, and what that would do is it would move the R13 register's contents to the R12 register's contents, right? So with floats, maybe do a comment here. GPR, aka int registers. Oh, my spelling. And then when we're using floats, we just have to use different instructions. So move SS, and then you can do XMM0 and then XMM1, and what that'll do is it'll move the contents of the XMM1 float register into the XMM0 float register. And what's this extra thing right here? Because we used to just have MOV, and now we have this suffix at the end of it, SS, or also in some cases SD. So for starters, in this video, I'm not going to talk about manipulating multiple pieces of data at the same time with one instruction. I'm just going to talk about one instruction. We'll just manipulate, one set of operands at a time, and that's it. You can sort of turbocharge the performance of your assembly programs if you're working with, I guess, graphics or, giant arrays or something like that. If you actually use one instruction to manipulate many registers at the same time or many pieces of data at the same time. So that would be a different instruction. It would look like MOV and then another letter and then the S or the D after it. So just basically understand that now this first S means we're gonna manipulate a single piece of data, or I guess a single set of operands, or one instruction per one thing that we're doing. Think of it that way. So all these are going to be S's. So it's always going to be move S and then another suffix after that. The difference for the last part of the suffix is whether you're going to be moving single precision or double precision. So remember, single precision floating point numbers are 32 bits. Double precision floating point numbers are 64 bits. So basically, on line 6 here, if I'm going to move with the S at the end, let me bring that back to the instruction so it's actually normal. On line 6, this basically means you expect only a 32-bit float single precision, and that's what you're working with. Whether you're moving data or multiplying or dividing or converting or whatever, you expect for it to be treated as a 32-bit float. Remember, the way the floats are laid out, it's not just that you get more bits and thus a higher value that you can represent. When you get more bits, then different bits are designated for different uses within the representation. So it's very important to use the right instructions, because if you try to interpret a single precision as a double, then the usages of all the different bits are not going to line up. The layouts are going to be off. And so then you'll end up with nonsense data. So most of this video, actually all of this video, we're going to be using double precision floats. So that's why at the end of every instruction, you're just going to see SD. So we're going to do a single set of operands for a single instruction, and then we're going to just use a double precision floating point number. So keep that in mind. So this is how you move one float into another. Okay, scroll down a little bit. Here's like that MOVSS that we talked about. Here's some sample code here. If you need to convert one type of float to another, like if you need to convert a 32-bit float to a 64-bit float or vice versa, then some of these instructions will help you. CVT basically, and then the designation of a single piece of data, single precision, to single piece of data, a double precision that would convert a 32-bit to a 64-bit float, and then vice versa the next one. You can just sort of see CVT and then SD to SS kind of tells you that's what the instruction does. We're not really going to do that in the code, but it's important to understand that you can, and all you have to do is look in all these tables here. Let's see. What we're going to do in the code that I'm going to write pretty soon is we're going to convert from floats to integers. Actually, I think in the code we're going to convert integers to floats and not back again, but you can just by looking up this. Let's see. Convert a scalar double precision. So here, this instruction, convert a double basically to an integer. We're not going to do that in the video, but here's how you do it. You'd say CVT, and then you would just look at the types. Single piece of data, double precision to a single integer. And then what we're actually going to do in our code is we're going to convert an integer value to a double. So actually not even this instruction. You can see, again, CVT convert, and then single integer to a single precision, to a single piece of single precision. So we're not going to use that. We're going to use basically this with a D at the end of it. So if we scroll down a little bit more, convert single integer to a single piece of data, which is a double precision floating point number. So that's going to show up in the code that we write in a second. And then, the arithmetic instructions are really, really easy. They're not as hard as the integer arithmetic instructions. If you want to just add two floats together, you just go add SD. Done. Where's the multiplication? Oh, we have adding, subtracting, which is easy. There we go, multiplication. You probably have had nightmares about multiplying integers or dividing integers in the past because you had to line up all those bits in two different 64-bit registers before doing anything or after doing anything. Notice how in floats, all you have to do is just say multiply, single piece of data, double precision, and then just provide two operands. Just two different float registers, or maybe one float register and a memory location, or whatever you want. It's really, really easy. There's a lot of sample code in this book. I'm just going to close this now. Or you can take the square root. I'm just going to close this now so that we can start writing our own code. Okay. Close this. And now I've got a little, a little code repo set up. I don't have anything in my assembly source code file, so we're going to write that together. Let me just double check. We're at 16 minutes right now. This video is going to be long. Okay, so what I want to show you first, I guess I'm not going to show you the makefile because this is not a video about makefiles. Again, if you want to know how to compile, assemble, link, generate makefiles, understand hybrid programs and drivers and things, all that is going to be covered in another video, or was covered in another video. So just trust me in this video for now. We have a makefile that just sort of compiles a hybrid program. We're going to have a driver, which is just a C++ program. And all it does is just, basically say hello. and then it asks for a double return value from a function that returns a double. That function called floater is going to be our assembly module, or it's going to be inside of our assembly module. Then it's just going to print the value it received and then just exit. So that's all it does. And we have an xtern-c module to disable name mangling so that our C++ module can call on an assembly function. So if we go inside of our assembly source code file, there's nothing. Again, if you want to know the basics of YASM assembly, see my other videos. For now, I'm just going to paste in a bunch of code and just quickly talk about it. So we have a data section here, and you can see all I have up above is just a bunch of strings. I'm just going to print, hey, give me an integer. Here's the integer that you entered. Now give me a float, please. And then here's the float that you entered. Oh, whoops, did I include my other thing here? Hang on, let me grab some code from somewhere else real fast. Doop doop. Man, there are like so many things. Okay, I gotta grab some of that. Long story short, this shared object helps me print and input floats and integers. You don't need it in order to understand what's going on. You could just inspect your program with GDB, which I already have another video on, or you can use a different library, or printf or scanf, whatever you want to input and output floats. So, but I just like to use that one. So your mileage may vary. Anyway, so then I have a CRLF because I like to be able to just kind of call a function to get a new line. And then we have some variables to hold our floats. So since we're going to be using 64-bit floating point numbers, that means they're 8 bytes, which means they're a quad word. So when I'm declaring my floating point numbers in the data section, I can just say DQ for quad word, and it will work the same as our integer memory locations. The only thing that's different is when you're initializing a value, you have to put a decimal point here. Unless you intend to totally erase the initial value, the moment the program starts, you'll end up with some really, really bad data if you don't put a decimal point here. So for example, if I made the mistake of saying, let's have a float multiplier, and we'll make it a quad word, and it'll be the number 3, and then later I try to use that as if it were a float, it will not work at all, because the system is going to see the 3 without a decimal point, and it's going to assume that I mean 2's complement for assigned integer. So then it's going to stick a number in that memory space that looks and works like an integer, and then later I'm going to try to multiply that as a float, and the result is going to be totally bizarre. It's not going to work. So make sure that even if I wanted to multiply something by 3, just 3, I would have to put 3.0 to let the system know that the 3 value should be laid out in terms of a float and not an integer, not 2's complement. Okay, then I just have like system call 1 to print something to the screen, and then standard output, which is file descriptor 1. See my other videos if you don't know what that is. Now let's start the text section of our program. So for starters, I'm going to be using some functions from my external library that I talked about. All I'm going to do is just use my library so that I can print and input integers, and then so that I can print and input floats. That's pretty much it for that. So you can use scanf or printf if you don't have access to this library. Now let's program our entry point. So I'm going to do this. And so if you recall, in our driver, the driver was going to call a function called floater. We put it in the name demangling section, xtern-c, and we said it was going to have a double return type. So if we look back here, the function name is floater, just like what the driver was going to call on. So that's great. And notice how we're going to return some data to the caller, but we're not going to be using RAX. We're going to be using XMM0. Again, XMM0 is always the return register when your function returns a float. You might be wondering at this point, well, what about RAX? Is something going to be done with RAX? Well, in your higher level code, as soon as you say that you want a double from a function that is a double, or that it returns a double, the RAX register is just going to be ignored. It doesn't really matter. So return your data in XMM0 always when you are returning floats. Okay, so then I have a function up here called float convert tests and another function up here called CRLF. I'm just going to import some of my, I guess, busy work code that you don't really need to learn about in this video. So for starters, I'll mention it real fast just so that you know what's going on. But I explain in another video how to write a function called print null terminated string, just to make sure it's easy to print these strings. Notice how I'm not specifying the length of these strings in advance. I'm just tacking a null terminator on at the end. That's explained in another video. And print null terminated string relies on a function I wrote called string length, which you have in the C library also. I didn't write the one in the C library, I just wrote my own right here. And all this does is it just computes the length of the string based on a null terminator so that the printing function can just, take the length and just give it to the system call so that I don't have to pre-compute it. And then the CRLF function, all that does is it just prints out a new line basically using print null terminated string. Okay, so not really that much has happened. At least we know how CRLF works at this point. Let's comment this out and see if the program actually runs. Make run. Again, make files are covered in another video. Okay, so it works. It's just sort of like doing nothing, but it works. Let's go back up to my code here and we'll start the main function, float convert tests. So let me uncomment that and then I'm going to start it up. Doop, doop, doop. Okay, so float convert tests. So this is the start of the function. It takes no arguments, it doesn't return anything, and it just uses register 12 for the integer that the user is going to input. So I'm going to ask the user for input, and we're going to save that there. That means, well, first, because this is a function, I have to have a return statement. And if we're going to respect the ABI, R12 was marked as Callee-Saved, so we have to say this is the prologue. And we're going to do a preservation of R12 with a push pop pair. Pop R12, okay, so that's done. Next thing that we need to do is, well, okay, spoiler alert, this program's going to crash because of stack alignment. I have another video out already that talks about stack alignment and why your program might seem to mysteriously crash for no reason at all. The solution for this particular program is just, we'll push another nonsense value onto the stack so that the stack will be aligned, and therefore any calls to GCC related libraries won't just crash the entire program. So just trust me on this. If you don't understand, go see my other videos. So the first thing we're going to do inside of this after we've preserved R12 is just ask the user for an integer. So I'm going to use my print null terminated string function. I'm going to give it 2 arguments. I'm going to say, hey, here's a message that I want you to print to the user. Please print, please input a string. And we want to print it to standard output. If you don't understand function calls, see my other videos. And then I'm going to call on my library just to input a signed 64-bit integer from the user. And then I'm going to steal or save that inputted integer into R12. That's all I'm going to do for now. Let's run the program again real fast just to make sure that it works. I'm going to go clear and make run. Enter an integer, and then I entered it, and then nothing happened. Okay. So then the next thing I'm going to do is I'm going to grab a float from the user. So I'm just inputting 2 numbers right away. So same thing as before. I'm just asking the user with a printed message to make the program nice and pretty. Hey, could you please input something? Then I'm calling on a function to input a float from the user. And then I'm using my first floating point instruction here, MOVSD. So, think about what we said before. Move means let's move something. If there's an SD at the end of it, that means we're going to do, one thing for one instruction. We're not going to have an instruction that moves many, many pieces of data at the same time. And so that's where the S comes from. And then the D means double precision. So that means I'm expecting that XMM0 is a 64-bit integer, 64-bit float, and I want to move it into a memory location that I've created up above called the float. So, to be fair, earlier I said all of your floats, they should have a decimal point. Since I didn't actually use the float before setting it, I could have put any number I wanted here and it would have been fine because it would have just been overwritten at this point. So I'm now grabbing a float from the user and I'm saving it. And, you know, I guess I could have saved the, I guess I could have saved the float somewhere else. But remember, every time you make a function call anywhere, you should expect that the floating point registers have been destroyed because the ABI does not, the application binary interface, you know, the standard that we're using, it doesn't say that any of the float registers are Callee-Saved. So any function that you call, including system calls, is allowed to destroy the floating point registers. So I'm just saving it right away. Anyway, so let's just echo the integer back to the user. This is still pretty basic stuff. I'm just saying, let's print a message saying, here's the integer that you entered. And then I'm going to move R12, which was the integer that they entered, into the first argument. And then I'm just going to call my little function here with a CRLF. So this should work. Let me just double check that this still runs. Enter an integer, 75, let's say, and a float 3.4, and then the integer you entered was 75. And so that's all we have right now. Okay. We're getting a little closer to working with our floats. Echo the integer. So now let's convert the integer to a floating point number so we can start working with it against the floating point number. I'm going to just paste my code here and explain a little bit. So we're going to convert the integer to a float and then multiply the float by a float multiplier number. If you look up at the top of our source code, I just put this number in here just because I felt like it, you know, float multiplier 3.333. And so what's going to happen now is we're taking R12, which was the user's integer input. We're going to move it into XMM0, and then we're going to use the convert instruction that we looked at earlier. So CVT means let's convert something like between float or whatever. And the first operand should be, sorry, the source should be a single integer. And then the destination will be a single double precision floating point. And then the 2 in there just means convert one thing to another thing. So convert a single integer to a single double. Single double sounds weird, right? But at that point, we should now have the user's input inside of XMM0 instead of R12. And the reason for that is, you know, we want to be able to multiply two floats against each other. We can't directly multiply an integer against a float. We have to do some conversion first. So that's why we have this here. Anyway, now that we have the user's input as a float, we can multiply it by other floats. So again, just MUL for multiply, and we're going to do a single piece of data, and it's going to be a double precision floating point number. And basically, I want to take that float multiplier that I set up above and multiply it against the float converted user's integer input and then get a result. I'm going to grab the result. The result is going to be in XMM0. If you haven't seen my other videos about the basics of assembly, go see them now. But basically, you should know at this point that if you only have two operands with this sort of function, then the first operand is not only going to be part of the source, but it's also going to be the destination. So XMM0 at this point in time now contains the result of multiplying the user's integer against the float multiplier, and we're allowed to do that because we converted their integer to a float first. We're going to store the result in a variable up above called the modified float. So if you look up, we just have like another quad word, call it the modified float. And again, because I stored it before actually trying to use it, I could have put any number here if I wanted to, but it, you know, it's just safer to stick valid floats in there at first. You never know how you might change your program and forget what you're doing. I do that all the time. So we've converted that and stored it. We've converted and multiplied and stored it. So let's tell the user what we've done. So we're going to basically print a message to the user that says, hey, here's the modified float. And then we're actually going to print it using my print float 64 function that I have. And again, you can use printf or whatever you want to actually print things. So we're going to use the move instruction for floats. And we're going to say, let's move a single piece of data. And we're going to move a double precision floating point number. And we want to move from the modified float to XMM0. And you may be wondering, what's going on? Why are we moving the modified float back into XMM0? Didn't we just have XMM0? Remember, anytime you call any function, all your float registers could be destroyed. So just simply printing a message to the screen, we already can't be sure that XMM0 is preserved. So that's why I saved it right away. And then I'm going to pull it back out right before I make this other call to print it. So remember, XMM0 is not just the return register for double returns or single precision returns. It's also the first float argument for function calls. So if I'm calling this function here, that's the reason that I loaded up the float into XMM0. I'm basically telling this function, you've got one argument, it's a double, here you go, please print it for me. Let's see if this actually works. I'm not sure if I need to add some more stuff. Okay, I think it should probably work. Okay, enter an integer, I'm going to say 11. Enter a float, let's say 2.1. And then it says the integer you entered was 11. And the modified float is 36.663, whatever. Let me double check that makes sense with a calculator that's taken forever to load. So if we did 2.1 times 3.3s, we end up with a 6. What did I do wrong? I think I misinterpreted my own code. We told the user about the modified float. The float was the multiplier. So we multiply their integer by the modified float. Oh, I think I multiplied the wrong number. Let me just fix that. So 11 times 3.3. Okay, so that's, yeah, the modified float is 36.66 whatever, and you can see that's the actual value. And so the program took the integer, it turned it into a float. You can imagine 11.0 now, and then it multiplied it by 3.3333, and then that's the number that we're seeing here. Okay, so we're almost finished. Tell the user about the modified float. The next thing that we'll do is we will multiply the integer by the float. So the user entered an integer and also entered a float, and we're just going to multiply them together, which you are allowed to do if you convert it first. So, excuse me. So we take R12, which was the user's original integer input, and we convert it back into XMM0. Remember, we lost XMM0. I guess we could have stored that somewhere if we wanted to, but I'm just going to convert it again with that same instruction as before. And then I'm going to multiply it, single piece of data, double precision, by the float that the user entered. So, if you scroll back up, we are storing their input right here into the float global variable, or I guess module global variable. So we're just saying the user's input multiplied, the user's input multiplied by the float, and then store that inside of XMM0. And then, sorry, my bad. We're converting the user's input to XMM0, and then we're multiplying it on that next instruction. And then finally, we're going to save the result somewhere. So XMM0 at line 117 now contains the result of multiplying the user's integer by the user's float, both things that they entered. We're just going to save it into this memory location, or this global. After we're done saving it, then we can pretty much just tell the user about it, and then we'll basically be done. Maybe I'll show you how to crash the program with stack alignment, just to prove to you that you should go watch that video. Anyway, so we're going to print to the user, hey, here's the result of multiplying your integer by your float. So just these 3 lines right here. And then we're going to take the float result that we saved. We had to save it because XMM0 can be erased just by one function call. So we grab it again from memory, we stick it into XMM0, and then we just print out the float. So basically, we're multiplying the user's integer by the float, and then we're telling them, here's the result, and then we're just going to print the result, and that's it. Let me see, is there anything else that I really need to show you? I think that might be it. Let's just make sure that the program works. So I'm going to do clear and make run. Please enter an integer, let's say 12, and enter a float 2.3, and then it's saying the modified float is 3.9, so I think that's what we kind of looked at before. The user's 12 input ends up being a 39 in float, but then if we multiply the 12 by the 2.3, then we get 27.6. The integer multiplied by the float is 27.6. So now we know how to do all sorts of manipulations between floats and integers and just floats against themselves. Notice how the driver, it received a value back from the caller. So like, you know, basically at the top right here in my like main area of this floater function, I'm just saying the modified float, let's return that to the caller in XMM0. And then when the driver said, I want a double value equal to the call of floater, that's how it got that. And then it just kind of printed it here. I guess maybe it would be more fun if we just stuck the int multiplied by the float in the return value, but I guess you probably understand by now. You can return any float that you want there. The other thing that I just wanted to do real fast before we stop is show you that we will probably crash the program if our stack is not in alignment. So integer and then a float, everything seems to work. But notice how if I take away this extra push pop pair, now the stack is going to be about 8 bytes shifted from where it was before. And that might not be good for the GCC libraries, which I think my float printing or inputting instructions might use. I got lazy and I think I decided to use printf or scanf or something under the hood for the float stuff, whereas I was doing it by hand for my integer stuff. So let's see. It should crash. 44 and then 4.4. Yeah, there we go. Seg fault. So again, mysterious crashes. If you are absolutely sure that your programs work, you might be a victim of stack alignment, and you probably want to go watch that video just to make sure you understand how to mitigate stack alignment issues when linking against GCC or using GCC calls or anything. Okay, so I think that's everything that I needed to show you. You are now an expert at the basics of floats. You can probably become an expert with just a couple watches of this video and a few read-throughs of that textbook and maybe some practice programs. So thank you for watching this video. I hope you had a little bit of fun and learned a little bit of stuff. I'll see you in the next video. Hey everybody. Thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community. So we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. You know, sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video. And it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? You know, just send me a comment, whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness, which is coming for us all.